So as I just mentioned before the video started, today is the last lecture on material balances. We might not get all the way through it because the quiz kind of chews up a little bit of time, but then we're going to move on to the thermodynamics portion of it. The objective of the thermodynamics is that it allows me to give you less information and you can still solve the problem, right? So we're relying less on some overlord giving you the specifications of the outlet, right? We're actually going to be relying on the real thermodynamics and the real physical properties of materials to give us more of that insight, right? So the objective is that we are getting ourselves closer and closer to what real chemical engineers have to deal with, which is we can control pressure and temperature. And that's basically it, right? If we want to increase the flow rate of something, we increase its pressure, it flows faster, right? So that's what we're really going to be doing, and so we need to sort of figure out how these different chemicals interact with one another. All right, so today is combustion. Right? Combustion provides most of the world's energy at the moment, right? So if we need energy, we usually just burn something. So what we're going to be talking about with combustion is no different than what we covered on Wednesday, where we had molecule balances, extensive reaction, and atom balances. The only difference between combustion and other reactions is that there's a different set of nomenclature that we have to go through, but the strategies are going to be the same, right? The atom balance is going to be the king or queen when we deal with combustion because we're not necessarily going to know the exact formula for the fuel we're going to be burning, right? But we don't actually have to know that. So in combustion, we can take solid carbon plus oxygen and react it to make CO2. Let's get all the reactions here. This is a side reaction that is not desirable. Carbon plus 1/2 oxygen can go to CO. Right? This is in the case of incomplete combustion, so it's not what we want, but sometimes it can happen. Any sulfur that you have in the system will react to form sulfur dioxide, and any hydrogen that you have in the system will react to form water. So we don't necessarily need to know what the formula is. Right? So let's say we have something like propane, C3H, it's 8, right? We don't have to necessarily think of it like one molecule. We can rip it apart into 3 carbons and 8 hydrogens and then use these reactions to figure out what they're going to go to. Right? So in combustion, we're not going to necessarily be burning a fuel where we exactly know what the composition is. So when we're burning a fuel, you'll get a weight percent of the fuel for every element. You can convert that to a mole percent. Then you take a basis of, let's say, 100 moles of my fuel. You'll know exactly how many moles of carbon atoms you have, exactly how many moles of hydrogen atoms you have, and you know that for every 2 hydrogen atoms, you use 1/2 of an oxygen molecule. Does that kind of make sense? Right? So we don't have to have this formula here, because when we do an atom balance, we're exploding it into atoms anyway. So when we think about combustion problems, we should be thinking about exploding the fuel into its individual atoms and then rearranging it into carbon dioxide, sulfur dioxide, and water. Those are the products we're making. Yes?
So every time you burn hydrogen, you're creating like water vapor as well?
Yes. So if you're like, so that's why they say, oh, hydrogen's like perfectly clean burning fuel, right? Because hydrogen reacts with oxygen just to form water. So the product of the hydrogen combustion is only water. What they don't tell you is that in order to make hydrogen, we use the syngas reaction process, which still burns methane, right? So syngas reformers, what you do is you react methane with water to form hydrogen and carbon monoxide. That's the syngas process. It's a very, very large commercial industrial process to make hydrogen. So if you need large quantities of hydrogen, you just burn methane to make CO2. But you do it in a clever way that it makes hydrogen as an intermediate. Yes?
How do we determine the ratio of carbon dioxide to carbon monoxide?
So this is what we want when we say complete combustion. This is incomplete combustion. Anytime we do calculations that require us to know how much oxygen we need to burn something, we always use complete combustion. we forget that this reaction exists. In this class, we love to throw in this reaction because it throws everyone off and it makes you do a few more atom balances, right? But in the real world, you may have incomplete combustion, right? Because these large industrial burners are huge. So there is still active research into how to design the injection ports, the shapes of the nozzles, what shape of flame do you want. That all helps us determine how we can reduce the amount of sulfur dioxides, or for example, NOx material. So nitrogen just goes to N2. So I'll add that one in here. Nitrogen just goes to N2. So ideally, nitrogen you just burn to form N2, but if you have incomplete burning, you can form NOxes, which are bad for air quality. Yes?
So would it be safe to assume that if oxygen isn't in excess, like when you're burning carbon, oxygen, carbon in excess, you'll get more carbon monoxide?
Correct. So for example, if you don't clean your home furnace, right, and something is plugged up and you can't get enough oxygen in the system, you can create carbon monoxide in your furnace, and that's why we all have, hopefully, carbon monoxide sensors in our homes. Right? But when we're having massive, massive, massive burners, this can become more of an issue, and for an industrial perspective, it's sort of wasted money. Right? And it's also poisonous, so we also want to avoid that as well. Okay, so this is the only new complication with combustion, and we've got a couple of other definitions, but basically when you see a compound like this, we can explode it into atoms. Oftentimes when we're burning a fuel, we do not know it's propane. We don't know it's ethane. It's just some fuel that we happen to purchase. And we may have an atom composition, and we have to be comfortable converting between a mass percent basis and a mole percent basis, right? Because moles react, masses don't. Okay? So another concept is what we call wet versus dry basis. Okay? So the purpose behind here is that when we're burning a fuel, we're making a lot of water. Water is unique among these chemicals. Okay, so we have carbon dioxide, carbon monoxide, sulfur dioxide, nitrogen, and water. What is unique about water compared to these chemicals?
It is a liquid.
At room temperature, it is a liquid. I would also accept that it is a subcritical fluid. So a supercritical fluid, we cannot condense it to a liquid, right, just by pressurizing it. So if we cool down a flue gas stream, which is the product of a burner, we can condense out the water. By condensing water, that's actually an exothermic process. You can recover more energy by condensing the water. So oftentimes when we're looking at the composition of flow streams, it's easiest to remove the water because it can be done just by cooling the stream down. These compounds cannot be removed just by cooling it down. They're supercritical fluids. Yes?
So you said water is a non-critical fluid?
Subcritical. Right? Carbon dioxide, nitrogen, they're all supercritical fluids. Like, so liquid nitrogen is 77 Kelvin at atmospheric conditions, so you got to cool it down very, very low in order to get it to condense. But water, room temperature and pressure, perfectly fine. We can get that liquid out.
What does exactly subcritical mean?
Subcritical means below its critical point.
Okay.
So that's a thing we'll talk about next week and also to death in your thermodynamics class. Right? But if you look at a PT phase diagram, right, it'll look like this. Low temperatures, high pressures, that's going to be a solid. Low pressures, high temperatures, that's going to be a vapor. And this little middle region, that's where we make liquids. The critical point is this guy right there. So if I go from here to here, I actually don't condense the fluid whatsoever. Right? So I can go from here to here, and I never boil the fluid. But if I'm below the critical point, and I increase the temperature at a constant pressure, I have a phase transition, which is that liquid-vapor equilibrium. So carbon dioxide, carbon monoxide, nitrogen, they all live in this region up here, so they're all supercritical fluids. Which means that if I try to pressurize the system, right, so pressurize the system here, I will not condense it to a liquid. I have to cool and pressurize to make a liquid. So that's what a supercritical fluid means. Okay? Don't stress about that one. All right, so air, we generally list air as 21%, 21% oxygen, and 79% nitrogen. That is not actually the truth whatsoever. Air is much more complicated. In reality, so this is approximation. Right, I'm going to put real here in quotation marks because I'm sure this changes, particularly with the carbon dioxide concentration. So 78.03, this is just based on some arbitrary time that whoever wrote this constructed it. 20.99% oxygen. Almost 1% is argon. We have 0.03% CO2, right? So about 300 parts per million. Maybe it's up to like 400 parts per million now. And then we have a very small amount of some other compounds of hydrogen, helium, neon, krypton, xenon, a bunch of other stuff. Now, the reason why we say this approximation is reasonably good is because oxygen is pretty close to 21%. Argon doesn't really react with anything, so we can easily lump it in here. CO2 is not really a concern for combustion, right, because it's already the product of it. So we lump all of these other things into the nitrogen because it's inert. Right? For most all of our processes, the nitrogen is just there along for the ride, particularly for combustion. Now, if I were to tell you that it was, this is not like Utah, but let's say it was a warm day in Miami, right, or Houston, how much percent water is in the air in a 100% humidity day? So 100% humidity, right? So sweltering heat, characteristic of the American Southeast. What percent water constitutes 100% humidity?
0.5%.
We have 0.5%. So we'll work that out, but for just right now, ballpark, yeah.
100%.
So you'll no oxygen, you'll just suffocate and die.
No, it's going to be like
It's 100% relative humidity, but what does that correspond to? We'll talk more about this, but just as an idea. So 100% humidity, right, is approximately 3% water. Right? So it's a relatively substantial amount. And if you're burning a lot of fuel with a particular air-to-fuel ratio, the amount of water can mess things up a little bit. Right? So there's a lot of reasons why we want to compare things on a wet and a dry basis. So what that means is that wet is going to be the composition including the water. Dry is going to be without. So all of these that I've written on the board, these are the dry basis for air. But based on whether you're in Salt Lake, Las Vegas, Phoenix, Houston, Charlotte, right? Those are all going to have different relative humidities, and it may affect your air-to-fuel ratio. So the dry basis is without water. Wet is with water. So the mole fraction of any species on a dry basis is going to be equal to the number of moles of species I divided by the number of moles of dry gas. So this is everything that's not water. The mole fraction of species I on a wet basis is going to be the number of moles of species I divided by the number of moles of dry gas plus the number of moles of water. So just to be clear, N dry is equal to molecules, not water. So this could be oxygen, nitrogen, CO2, SO2, dot, 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 dot. So everything that's not water is going to be your dry compounds. So the way to convert between a wet basis and a dry basis is we just build a table. Right? So we have a table here right? Compound. Okay, let's call it compound 1, compound 2, compound 3, dot, 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 and then water. Okay? We have the number of moles of species I, and whatever that composition is, da, 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 right? We can do total wet, or we can do total dry, right? And then the mole fraction, either dry or the mole fraction wet. Right? So just build a table. If we know how many moles of everything we have, because maybe we've chosen a basis, then we can add in how much water we have. We can add up all the wet things, so that's the total number. We can add up the dry, that's everything minus the water. And then you just divide the total number of moles, right? Ni divided by N dry, and this is Ni divided by N wet, right? So just build a table, be organized, assume a basis, and then we can easily convert between the wet basis and the dry basis. So one of the ways that this is convenient is because when we use this approximation that air is 21% oxygen, 79% nitrogen, that's a dry basis. So if we were to translate this information across regions, that would hold true. But within our specific region, we would want to consider what's the actual composition of oxygen based on the relative humidity, because you may need to adjust your air to fuel ratio if it's a humid day versus a not humid day. Yes?
So what does relative humidity mean? How do you convert between percent humidity to percent composition?
So relative humidity, and we're going to talk about this next week, is equal to the mole fraction of water divided by the mole fraction of water at saturation.
So what Todd said.
Was that?
That's what Todd said, like the max saturation.
Yes, so this here is going to be a function of water's vapor pressure. So the Y of water at saturation is going to be equal to the vapor pressure of water as a function of temperature divided by the atmospheric pressure. And this is going to be an application of something called Raoult's law. Do you guys hear about Raoult's law? You learned Raoult's law? Right, so this is just an application or simplification of Raoult's law. But this calculation is a vapor-liquid equilibrium calculation. So it's a multi-component, multi-phase calculation. But we're going to talk more about this, so don't worry about it. Just answering because of the question. Yes?
Side note, wouldn't 100% humidity just be rain then at that point? Wouldn't it mean it's saturated?
It could be, but it doesn't necessarily have to be. So when it rains, that means it's super saturated in the atmosphere. So for example, if you take a region of air, let's say, for example, like a big thunderstorm that happens in like the Great Plains area, like in, let's say Oklahoma or something like that, right? So you get a hot, really humid air coming from the Gulf of Mexico, travels north, and because of the Rocky Mountains, it sort of gets deflected up north, right? So that hot, humid air is at a relative humidity of 100% based on the temperature that the air picked up all that water. If it gets pushed up into the atmosphere or into colder air, or if air from Canada comes and meets it and chills it out, that lowers the vapor pressure of water, which means that it lowers what the maximum amount of water that can be in the air is. So then that means that your air is now supersaturated. That causes liquid to condense. That forms clouds. Those clouds get too heavy. They start to cry, right? And then that's where we get the rain from. Right? So when you have the hot, humid air meeting cold, dry air, or cold, wet air would be even worse, right? That's why we get these really big tornadoes and supercell storms sort of in the Great Plains. Yes?
For the mole fraction of wet, is it supposed to be dry plus wet in the denominators? Or is it just wet?
I just wrote N wet, but I could say N dry plus N H2O, which is equal to N wet. I'm being sloppy in my nomenclature.
So N wet is the total.
Yeah, that would be everything together. So N total could be N wet. Or you could do N dry plus N water. Yeah. Okay. So there's just a few more definitions before we can just knock out some examples. But again, the examples are the same as what we did. The only difference is if you don't know the chemical formula, you just fall back onto these reactions. Right? So how many total carbon atoms do you have? For every one carbon atom, you need one oxygen to make one CO2. Right? So you don't need propane. I can just give you a bucket of hydrogen and carbon atoms, and you can still tell me how much oxygen we need to burn that. Okay? Okay, so we have something called theoretical oxygen or air. And this is moles of O2/air for complete combustion. Okay, so this would be, for example, if I were to balance out a chemical reaction. Let's just make a simple one. Okay, so this is methane combustion. As a recap, let's just balance out this chemical reaction. Where should I start? Should I start with the, now this one's pretty straightforward. Actually, yeah. Carbon, if I have one carbon goes to one CO2. That's pretty easy. Now, if I did oxygen, I have oxygen, oxygen, and oxygen. No, I can't do that one. So let's do the hydrogen next. So I have 4 hydrogen atoms. That means I need 4 over here, so that's a 2, right? And now we could do the oxygen. So I have 1, 2, 3, 4 oxygen atoms, which means I need 2 oxygen molecules to do the complete combustion. Okay? Flashback to high school chemistry. So theoretical oxygen would be, if I have 1 methane, how many moles of oxygen would I need? 2. That's the theoretical limit. Okay, that's how much I need for complete combustion. Now, what would my theoretical air be? How much moles of air do I need for complete combustion?
Divided by 0.21.
Yeah, so it would be 2 divided by 0.21, right? Because that's the ratio of oxygen in our air. Now, if I had humid air, would I need more air or less air? More, because some of that is occupied by the water itself. Okay? So the difference between theoretical oxygen and theoretical air is, are you measuring how much oxygen you're feeding to the system, or are you measuring how much air you're feeding to the system? All right, so excess oxygen or air is equal to moles fed to the system minus moles theoretical, right? So remember, the moles theoretical is for 100% combustion divided by moles theoretical. Oh, times by 100, because this is usually in percent. Why would we want to feed more oxygen or air to a process than we need?
If you're realistically, if you feed the exact amount of theoretical moles, you're going to get a lot of incomplete combustion. If you have more oxygen, you're going to get less incomplete combustion. So that's more complete combustion and less incomplete combustion.
Correct. So if you have a burner, right, somebody actually has to design this thing, right? So where do you inject the fuel? Where do you inject the oxygen or the air? And unless at every point in space in this entire burner you have exactly a homogeneous 100% well-mixed system, you're going to have some regions that are oxygen lean or fuel rich. Right? So you're definitely going to get incomplete combustion in those regions. Right? So the only way that theoretical air works is if your system is 100% perfectly mixed. And that's not going to be how it's the case in reality. So you always want to put in a little extra air. Air, is it free? Yes. The only cost of air is the cost of a fan to blow it in the direction you want it to go in. Okay? What?
Has no one here seen the Lorax?
The air is free, right? No one is charging you to use air. Now, water is not free, right? Because water, you have to get some rights to it. But there's no rights to air. You just basically suck it out of the sky and then use it in your process. Okay, now what's the downside to using too much excess air? Let's go back here.
React with other things?
It could react with other things, but in combustion, we want it to react with everything. Back here.
Is it because it's harder to extract the heat out?
Yes, why?
Because now we have a lot of cold air that is kind of like saturated it with low heat.
So who remembers the Carnot efficiency?
I don't remember how it works, but I remember the name.
So what is the equation for the Carnot efficiency? No?
Oh, wait, I do remember this.
Back here at the green.
I don't remember the exact equation, but it's basically like the further the temperature differences, the less efficiency.
Yeah, so the Carnot efficiency is 1 minus T cold over T hot, right? So if you want to get a 100% efficient process, you either have to reject some energy to a reservoir that's at absolute 0 Kelvin, or you need to supply the heat energy at an infinite temperature. So if I add in more air, that means that some of the energy that is stored in those carbon-carbon and carbon-hydrogen bonds, when they break, that energy has to go somewhere. The reason why things heat up when you burn them is you break that bond and you release a ton of energy to the system. Okay? Now that energy gets absorbed by the molecules in the form of kinetic energy. So that chemical energy speeds up the molecules and they move faster. Temperature is the measurement of the average kinetic energy of the system. Right? We only actually learned of this in about the late 1800s and early 1900s. Right? So Maxwell-Boltzmann and the kinetic theory of gases is where we got the physical understanding for why temperature is the velocity. Now, if I have to break that chemical bond, and now I have to give that energy to 5 times as many molecules, each of them speed up a little bit less, which means that my burner is now at a lower temperature, which means that my efficiency of the process is going to go lower. So I want to do enough excess oxygen to make sure that I have complete combustion, but not so much that I'm lowering the temperature. Now sometimes, right, we actually need a very, very hot chemical process. So let's say, for example, in concrete manufacturing or making bricks, right, we need kilns that are hot enough that they can make chemical reactions occur on solid compounds. In that case, we may need to burn not even in oxygen, but maybe we need to burn, not in air, but in pure oxygen. Maybe just the presence of those nitrogen atoms are enough to cause problems. And indeed, this is a technology that people in the University of Utah are pursuing. Has anyone heard of chemical looping from Professor Kevin Whitty? Chemical looping combustion. So the idea is we extract oxygen from the air in some sort of a solid phase reaction with the oxygen. Then we release the oxygen next to the fuel. Then you burn the fuel in pure oxygen. That allows you to get to a higher flame temperature, increased efficiency, and the big advantage is that your product stream doesn't have any of this nasty nitrogen in it. Now, nitrogen is inert, but the problem is we cannot separate oxygen and CO2 trivially. So if we can burn our fuel in pure oxygen, that means the products are forming are only carbon dioxide and water. The water is easy to remove. We just got to let it cool down and the water will condense out. And then we've got a pipe of pure CO2 that we can then sequester into the ground or use for some other chemical process. But right now, if we're just burning stuff in air, even if we were to capture all of the flue gas, the product gas would be mostly nitrogen. So you would basically quadruple the cost of transporting that pipeline and quadruple the storage requirements because most of what you'd be throwing in the ground is just nitrogen gas. Right? Yes?
You said that nitrogen can sometimes form NOx. Is there like a chemical equation for NOx?
So that's a very complicated process of which I'm not an expert. The thermodynamic equilibrium is N2. That is the lowest energy state for nitrogen, but if you have incomplete combustion, you can still form NO2s and NO3s, and those are going to be contributors to poor air quality. So the design, like I said, of the little teeny nozzles that go into big industrial furnaces is still an active area of investigation. So we don't want to make NOx, so what people do, like Professor Sutherland in our research in our department, Professor Sutherland does large-scale computational fluid dynamics simulations of burners and flames to help investigate where should you inject the fuel, where should you inject the oxygen, and at what locations is, let's say, for example, NO2 and NO3 being formed. So the world is very complicated, and we're all chipping away at it slowly. Okay, so what I have left is, let's see, I have an example, but I may table that until Monday. But it's really just an application of these definitions. So combustion is just a subcategory of the reactions. The tools we have are identical. The nomenclature is a little bit unique, right? Because we say theoretical oxygen or air, that's enough we need for total combustion. So we should think of this as the stoichiometric ratio. Excess is the same thing as an excess reagent. But we just have, since combustion is such a prolific chemical reaction, it's developed some of its own nomenclature. So we'll do a quick example of some combustion reactions on Monday. I don't think we have any combustion reactions on the homework, right? I don't think so. Well, if everything's out of sync a little bit, like if I'm off by a day, then I can have homework problems of stuff. But I don't think we have any combustion problems on the homework.
The one here tonight?
Yeah. No combustion, right? But there's still chemical reactions. All right. Wet and dry basis, right? Again, just a nomenclature. It's a matter of convenience. And yeah, so after we finish this example, we are shifting on to thermodynamics, okay? So we're going to talk about equations of state, vapor-liquid equilibrium. So we're going to take what we know now and expand it aggressively, right? So the problems are going to get a lot more complicated, but the tools will stay the same. So it's just organization and lots of algebra for the material balances. Okay, have a good weekend.